The Earth. Let's take a look at our planet on a new scale, a billionth of a meter, a nanometer. Suddenly, it seems to have grown immensely. An equally radical revolution has been brought about by nanosciences and technologies. Distance between the Moon and the Earth, on the order of 1 billion meters, a day's travel. The distance between a meter and 1 billionth of a meter, roughly the same gulf, but taking just a few seconds. Now we're heading deep into the world of nanoscience, down to the dimension of an atom. To understand today's scientific nano-revolution, we must first take this plunge into a sea of atoms. New landscapes, new sensations. This hidden world surrounds us at all times, on every side. Each white ball is a cloud of electrons, concealing an atomic nucleus. You're about to discover how scientists have reached this frontier, the land of the atom, and opened up an infinite new field of research and practical applications. Like others, this research institute is already producing applications based on assembled molecules barely 10 nanometers long, nanoparticles. Here are a few little experiments demonstrating product efficiency before and after, just like the old hair restorer ads. On the right of the picture, a normal paint job. On the left, a coating containing new, improved nanoparticles. Now this car door can't be scratched. Neither can these glasses, which grow darker as light gets stronger. A music CD can be engraved on this flexible plastic sheet. The nanoparticles on this surface repel water and make this surface hydrophobic too. Spraying graffiti here is a waste of time. No need to scrub. The paint just slides off. Straw and wood no longer burn. Firefighters can rest easy. The reason for these phenomena, almost magical on our scale, is the shared property of all these objects, nanoparticles at the surface or inside. To understand how industry can manipulate these molecules on the nanoscale, we'll begin at the beginning. For the observation of particles no bigger than a few billionths of a meter, researchers invented a new microscope, only to discover that it could manipulate atoms too. With this tool, seeing is touching. Like a blind man's probing stick, the tip of the microscope feels the atoms to display their contours.
On voit déjà d'ailleurs que le petit palpeur doit avoir à peu près les mêmes dimensions que les objets que l'on va regarder, et on va déplacer cette pointe sur la surface, très très proche de la surface, pour enregistrer les interactions entre la pointe et la surface.
In this animated sequence, the tip, made up of atoms, is bathed in a blue glow, linking it to the surface observed. This glow represents an exchange of electrons between the surface atoms and those forming the tip. On this scale, the atoms can swap electrons. This is what happens as the tip of the microscope moves. With a scanning microscope such as this, pictures on the screen do not represent light, but rather computation. They are actually a measurement of electron flow voltage and intensity, changing with every movement across the measured atoms. This provides a sort of relief map of the surface examined, atom by atom. To sum up, We think of atoms as spheres, but in fact they're made up of a nucleus surrounded by a number of electrons in orbit. No surprises there. However, brace yourself for a shock. No scientist can say with certainty where an electron will be at any given moment. In fact, an electron doesn't revolve around a nucleus on a fixed orbit like a satellite around a planet. Instead, it may be at any point around the nucleus at any given time. It's as if it were everywhere at once, forming a sort of electronic cloud, a sphere in fact. This is one of the basic consequences of quantum physics. From time to time, an electron may happen to move a little further from its nucleus than usual. Since there's necessarily another atom close by on this scale, the electron sometimes finds itself in the cloud of electrons of this other atom, having broken through the barrier that held it around its own nucleus. This electron transfer is what we call the tunnel effect. By generating a stronger electron flow through the tip of the microscope, a given atom can be attracted. This tool that can feel matter and thus give us an image can also sculpt it. By gouging out atoms, it can etch lines. These 4 white marks are an electron microscope image of the molecule, and here is a more detailed representation. Pushed by the tip of the tunnel effect microscope, it moves, rubbing against the surface. Successive images are needed to check that it has really been displaced. Mission accomplished. To make this movement more precise, researchers are trying to modify the initial structure of the molecule by adding paddle wheel extensions. At this point in the story, prospective nanoscience applications are appearing before your very eyes. Now we can dream of imminent and more long-term applications, and note that nanotechnologies are already used today. Let's look at a last concrete example, beginning with a standard industrial-scale chemical reaction controlled on the nano scale. Take iron chloride and mix it with water to give this orange color. Add caustic soda. Leave the combination to react for a few minutes until it turns black, showing that iron oxide crystals have formed. Above all, don't let the source go lumpy. Particles must be kept down to a scale of a billionth of a meter. Of course, the exact recipe is a closely guarded industrial secret. To simplify, let's just say that each particle is positively charged so that they repel each other. Here's the lowdown. On the left is the magnetizable particle, on the right, an AIDS virus antibody. They bind together because of their positive and negative charges. If the virus is present, the antibody recognizes it and sticks to it. Then the magnetizable nanoparticle is extracted, still bound to the virus. This early AIDS screening method is still in its development phase, but the example shows what a wide variety of roles nanoparticles can play, particularly in the biomedical field.